In this video, we'll go through the process of calculating an F-test for a simple one-way analysis of variance. Note that we're using very simple numbers and ridiculously small samples so that the calculations are more straightforward and clear. To keep things simple, we'll only have 3 groups with 3 people in the first group and 4 people in the second group and 5 people in the third group, all right? Now, as we've discussed in previous videos, calculating an F-test for a one-way ANOVA involves calculating a sum of squares, a degrees of freedom, and a variance for both between groups and within groups, right? Now, to help organize all of those values, ANOVA results are often presented in variations of this type of a table, which is often generically referred to as an ANOVA table. Now, we're going to see this a lot. For now, notice that I've X'd out all of the values that we're going to calculate in this video, right? So we'll first look at the raw data and then go through the process of filling out all of the values in the table. So, as I just said, to calculate an F statistic, we need to start with the raw data. So here I've organized the data into 3 columns, each column corresponding to one of our 3 groups. And if you look carefully, you may notice that the scores do seem to be a little different from group to group. But, given the samples are small and the range of variability that we see in the scores, the F statistic can help us to estimate the probability that we would have just randomly seen those size differences if in fact the means for those 3 populations were the same, right? So let's do our F-test, and again, that will let us see the likelihood that we would have seen those differences just randomly by chance if the populations those 3 groups reflect in fact have the same means. So let's first sum up the values for each group. If we do that, we see 1 plus 2 plus 3 is 6, and 3 plus 4 plus 5 plus 6 is 18, and 5 plus 6 plus 7 plus 8 plus 9 is 35. We then calculate the means for each group by dividing each of those sums by its respective n. So the mean for group 1 is 6 divided by 3, or 2, and the mean for group 2 is 18 divided by 4, or 4.5. And the mean for group 3 is 35 divided by 5, which gives us 7. Now, in addition to the group means, we also need to calculate the grand mean for the scores. Now, because the sample sizes are not equal, we need to be careful to actually calculate the mean based on the 12 original raw scores. And don't just take the average of those 3 group means. It won't work. Look at all the 12 raw scores, add them up, calculate the mean. Now, doing that, we find that the grand mean across all 12 scores in this case is 4.917. All right? We then focus back on the group means and subtract the group mean from each of the scores in that group. So we subtract 2 from every score in group 1 because 2 was the group mean for group 1. And we subtract 4.5 from all 4 scores in group 2 because 4.5 was their mean, and we're going to subtract 7 from every score in group 3 because 7 was the group mean for group 3. If we do that, this gives us the deviations from the group mean. Now, our next step is to square each of these deviations in order to calculate the squared deviations from each group mean. We then add those squared deviations to obtain the sum of squared deviations for each of the groups, which we then add up to obtain the sum of squared deviations within groups, or for shorthand, just the sum of squares within. All right? Now with that, we can enter our first value, the sum of squares within, into our ANOVA table, right? Let's do it, right? Now, back to our calculations. The degrees of freedom within is simply the total n, 12 in this example, minus the number of groups, which if you remember we call k. Now in this case, k is 3 because we have 3 groups. So using this very simple data, our degrees of freedom within is therefore equal to 12 minus 3, which gives us 9. We can then enter that into our ANOVA table, all right, and let's keep going. So finally, at least in regards to the within group calculations, we calculate our variance within. And remember, you may see this reported as the variance within or the S squared within or just called the mean square within. But it's the same thing. It's the within groups variance. And we get that by dividing the sum of squares within by the degrees of freedom within. So in this case, it's 17 divided by 9, which gives us 1.889, our within groups variance, or variance within. All right, so let's put that into our ANOVA table as well. Now, with that, we've completed the within groups calculations, so let's start to work on the between groups calculations. The first thing we do is go all the way back to our group means. Remember the 2 and the 4.5 and the 7 for each of our group means. We then subtract the grand mean, which was 4.917, from each of those group means. To see that, let's list the 3 group means, okay? Like I said, we subtract the grand mean of 4.917 from each of these values. That gives us 2 minus 4.917 and 4.5 minus 4.917 and 7 minus 4.917, right? If we solve those, that gives us our group mean deviations from the grand mean. Let me repeat that. It's a mouthful, isn't it? It's the group mean deviations from the grand mean, which are negative 2.917 for group 1, negative 0.417 for group 2, and 2.083 for group 3. We then square these group mean deviations from the grand mean. We square each of those, right? And that gives us 8.507 for group 1, 0.174 for group 2, and 4.340 for group 3 as our squared group mean deviations from the grand mean. Now remember, when we discussed partitioning the sum of squares, these values, the the squared difference between one's group mean and the overall grand mean, those values applied to every person in the data set, right? Every person in the data set has that deviation squared, right, associated with them. So we have to weight each of these values by the number of people in the corresponding group. So each of the 3 people in group 1 has a squared group mean deviation from the grand mean of 8.507, right? That applies to each person, so each person has that deviation between their group mean and the grand mean squared. So 8.507 for all 3 people. And if we add up those 3 8.507s, we get 25.251. Similarly, each of the 4 people in group 4 has a squared deviation between their group mean and the grand mean of 0.174. Each person has that 0.174. So we add that up across all 4 people, and we see that sums to 0.694. Right? And each of the 5 people in group 3 has a squared group mean deviation from the grand mean of 4.340. Right? Across all 5 of them, that sums to 21.701. And yes, if you're following along at home, you may get slightly different values than I'm getting. That's because I'm using the unrounded values. But again, within rounding, this is all good, right? Let's keep going. We then add these squared deviations to obtain the sum of squared deviations between groups, or the sum of squares between, which is 47.917 in our example here. We can then put that into the ANOVA table, right? And we're ready to keep moving. Now, the degrees of freedom between is simply the number of groups. Remember, that was k, equal to 3, minus 1, which in this data works out to be 3 minus 1, which is 2, right? So let's enter that into the ANOVA table as well, and we'll keep plugging along. The last step for our between groups calculations is to calculate our variance between. Now, as with the variance within, you may see this reported as the S squared between, or the variance between, or the mean square between, but it's all the same thing. It's the between groups variance, right? We get this by dividing the sum of squares between by the degrees of freedom between, or in this case, 47.917 divided by 2, which gives us 23.958. Again, with rounding. And again, remember, I'm using non-rounded values, so if you've rounded, you may get slightly different values. And again, that's okay. So let's add that to our ANOVA table, and you can see we're steadily deriving all the information that we need for the ANOVA table. With this, we're now ready to calculate our F statistic. To get that, we just divide the variance between by the variance within, which is 23.958 divided by 1.889, which gives us an F of 12.684, right? We can then add that to the ANOVA table, and we're almost done. But a couple things before we wrap up. First, remember to report F using the proper notation. Don't just say F equals 12.684. No, use the proper notation. Include the degrees of freedom and report it as F parenthesis 2 comma 9. Put those degrees of freedom in the parentheses, right? F parenthesis 2 comma 9 equals 12.684. And that looks beautiful, doesn't it? All right. Also, while we're here, let's just enter the last cells for our ANOVA table, and these are pretty easy. Okay, first, the total sum of squares is just the sum of squares between plus the sum of squares within, which works out to be 64.917. And the degrees of freedom total is just the sum of the degrees of freedom between plus the degrees of freedom within, or 2 plus 9, which gives us 11, right? Right. So there we have it. That's how you calculate an F statistic and complete the ANOVA table if you're doing a one-way analysis of variance. To obtain your p-value, all you need to do now is enter the F statistic, that 12.684, and the degrees of freedom of 2 and 9 into Excel or some other software, or look it up in a book, and find what the p-value is. Right? Hope you found this helpful. All right. Take care. Bye-bye.